In this video, we're going to look what happens to small angles measured in radians, particularly looking at what happens to sine theta, cos theta, and tan theta. Now, in order to do this, we need to consider this diagram. So we have a circle, center O with radius r, so this circle here. We have a point T outside the circle, and a line joining up to this point here, P, which so this line is a tangent to the circle at P, and the tangent radius property says that this must be 90 degrees. And then we have a sector OPQ and a triangle OPQ. Right, what we need to do in order to do this, we're going to look at the areas of triangle OPT, sector OPQ, and triangle OPQ. So we need to find this length here. So using tan of this angle here, theta, measured in radians, is going to be PT divided by R. And if we rearrange that, PT will be equal to R tan theta. Now the area of triangle OPT is bigger than OPQO is bigger than triangle OPQ. Right, now the area of the larger triangle is going to be used a half base times height, so it's going to be R times R tan theta divided by 2, so it's going to be a half R squared tan theta. The area of this sector here is going to be a half R squared theta. Okay, and the area of this small triangle here, using two sides and include the angle, it's going to be a half of R squared sine theta. Right, obviously the half R squared can cancel out. Remember that theta is measured in radians, so all those can cancel out. So we're left with the idea that tan theta must be bigger than theta, which must be bigger than sine theta. Now, if for small theta, and for this we'll go to an applet, and the applet I will include in the link to the applet I will include in the notes of this video. So we've got the same situation here. So we've got that tan theta is bigger than theta, which is bigger than sine theta. At the moment, tan theta has a value of 2.57 for 1.2. The angle's 1.2, and sine theta is 0.93. Now, if we make theta smaller by moving the slider, okay, look what happens to these three angles here. What happens is that as they get smaller and smaller, the large triangle and the sector and the smaller triangle will all coincide, and therefore we will get that these will approximately come equal. So at the moment we've got 0.4, 0.38, 0.37. Obviously the smaller we make it, the better. Now it's basically they're now all saying the same thing, 0.19 for a very small theta, because what's happened is that the three things have now coincided. Okay, and therefore we can now say that for small theta, that tan theta is approximately equal to theta, and also that sine theta is also approximately equal to theta. Again, I'll put this applet in the notes of the video. There are a few other things here that you can click on if you want to try it for yourself. Okay, but for small theta, you're going to have that tan theta is approximately equal to theta, which is approximately equal to sine theta. So that's the first thing. So now, what about cos theta? Well, if we place a triangle, a right angle triangle, on the unit circle, that means that the radius here is 1, and the distance OQ will also be 1. Okay, then if this distance here is 1, this length here, OR, is cos theta, and this length here is sine theta. Again, don't forget theta is measured in radians. Okay, because sine is opposite over hypotenuse, which is sine theta over 1, and cos is going to be adjacent over hypotenuse, so it's going to be cos theta over 1. So this length has to be cos theta, this is sine theta if this hypotenuse is 1. Right, so we have an arc here, PQ. So arc PQ was equal theta from the definition of radians. And remember, if the angle here is theta measured in radians, and this is 1 and this is 1, this length here has the same length as theta. That was the definition of radians. Now, if we draw in the line PQ, we get a straight line here, okay? And then if we can now consider the triangle PQR, this small one here, this length here is 1, therefore the distance RQ or QR is going to be 1 minus cos theta. That's 1 minus cos theta. Right, now, and if for small theta, this arc and this line will actually coincide. So we can say that the distance PQ is approximately equal to theta as well. And now, if we now apply Pythagoras' theorem to this triangle here, we're going to have that RQ squared plus RP squared is equal to PQ squared. Now, RQ is 1 minus cos theta, so it's 1 minus cos theta all squared. RP is sine theta, so it's going to be sine squared theta, and PQ, because these two now coincide, this is theta squared. If we now expand that, we get 1 minus 2 cos theta plus cos squared theta plus sine squared theta is equal to theta squared. Now, if you apply Pythagoras to this triangle here, you're going to get that cos squared plus sine squared is going to be equal to 1 squared. So we have a relationship that says that sine squared theta plus cos squared theta is equal to 1. That means that this bit here I can now make be 1, and 1 plus 1 makes 2. So we're going to have 2 minus cos theta is equal to theta squared. And remember, we're trying to find a value for cos theta when theta is small. So 2 cos theta will be 2 minus, approximately equal to 2 minus theta squared. Dividing through by 2, cos theta will be 1 minus theta squared over 2. Remember, this only really works when theta is very small. So, for small theta measured in radians, sine theta is approximately equal to theta from the previous part. Cos theta is 1 minus theta squared over 2. And tan theta is approximately equal to theta. And these results need to be sort of remembered. So for theta measured in for small theta measured in radians, and we're talking about like theta being between like minus 0.1 and 0.1, then sine theta will be approximately equal to theta, cos theta will be 1 minus theta squared over 2, and tan theta is approximately equal to theta. Okay, so this has been a video to show you why for small angles measured in radians we have these results. I hope you've understood, and I thank you for watching, and I remind you that the GeoGebra applet is in the notes of the video. Thank you very much.